Hello, everyone. Welcome to the Guaranteed Safe AI seminars. I'm Orpheus, founder of Horizon Events, a new nonprofit agency focused on events for AI safety research and development. So the purpose of the seminar series is to facilitate progress related to the Guaranteed Safe AI research direction. Today, the format is 1 hour, starting with Evan's talk, followed by Q&A and discussion. We aim to start and end on time. During the presentation, you can write your questions in the chat. In the Q&A, we ask you to raise your hand. The event runs on a monthly basis. Next month, in August, we will start having a monthly social mixer event in addition to the seminar one. So yeah, today's speaker is Evan Miyazono, founder of Atlas Computing. Their mission is to foster an ecosystem to advance safeguarded AI, a new architecture that provides quantitative safety properties. The session is titled Proving Safety for Narrow AI Outputs. So thanks, Evan. The floor is yours.
I'm Miyazono. Thank you so much for having me. And I won't speak much as to my background. Happy to answer like what qualifies me to do these weird things. In the Q&A session, I'm going to try and target a roughly 30-minute talk and have a lot of time for discussion Q&A. And I'm delighted to see that Xiaowei is here. So I think that we'll be able to have some deeper discussion into some of the things, even if I am not sufficiently familiar with a technical detail or two. But I'll be talking mostly about what I'm doing at Atlas Computing. I like to say that what we're doing is primarily scaling human review. I think this is a really easy, simple, and straightforward way to explain both what we are doing, but also kind of what Guaranteed Safe AI is doing generally. One of the things that I love emphasizing is that we are seeing AI move forward, contributing to multiple fields, and you see the same capabilities improving the complexity of the outputs across different areas. And for simple review, like, is this image what I want? It's easy. And in a lot of, or for more sophisticated outputs, if you extrapolate trends, review of these outputs gets much harder to the point where you might expect review to, in many cases, be skipped, especially in instances where the cost of a human's output is roughly 10 cents an hour equivalent. And I think in this world, you end up with an arms race using something like profit as a proxy for good, or you essentially have something that looks like a weaker form of misalignment, even before you end up with the risks of a stronger form of misalignment. I find it very useful when speaking to people who don't understand who are unconversant with, and maybe not convinced by the Guaranteed Safe AI framework or framing, explain to them the possible risk that you could have a future where we see dramatic acceleration of progress with AI in manufacturing, construction, clean energy, robotics, automation, software generation. And these things start feeding into each other, and you start ending up automating increasing fractions of the economy. And then at some point, something breaks in an unexpected way because we don't have scalable understanding of the changes we're making to systems. So maybe that's a new solar fuel process that creates some byproduct that inhibits photosynthesis. Maybe this is in corn and we have famine, or maybe this is in algae and we have mass extinctions. Or we have a new geothermal energy system that somehow destabilizes supervolcanoes. I'm not saying that these specific examples are particularly plausible, just that there are likely systems that we are going to disrupt because we're not improving our understanding of systems. Other architectures, mainstream architectures for AI, are finding better ways to propose creative changes to systems rather than understanding robustly the framework of the system. So if you're trying to justify guaranteed safe AI, I would definitely recommend taking a framework, trying an argument like this, seeing how it works in terms of convincing people that this is a valuable direction. The solution that we're proposing is this hyper simplified and well scoped pitch of don't try to optimize or don't try to encode what your values are, what the optima you're trying to maximize is. Try and specify constraints in the same way that in the rest of society we set laws, and we don't tell you how to behave very normatively. We have conventions that you may or may not flout, but we have laws and we evaluate in a fairly scalable way with the size of the human population, whether or not individuals seem to be violating those rules. And we can bring the analog into this, into the automation space for various domains. And so I think this is probably intuitive for people who have thought about implementing guaranteed safe AI architectures, that you could do this in a narrowly scoped way, but making tools to set the rules that AI proves obeying seems to be a very good way of explaining to people unfamiliar with these types of architectures or approaches how to go about this. That's kind of the rough outline of the problem we're trying to solve. And when discussing Atlas Computing's approach, feels like it, at least there might be one or two people here who have not come across this paper because it is the name of the seminar series. I would hope that this is familiar, but I think that the idea of setting rules or making tools to set rules that AI proves it's obeying does in fact match the auditable world model, having a specification for safety in terms of that model and verification against those specifications in that world model. For those of you who don't know, I used to work with Davidad. He got me into all of the into this problem. He is leading this safeguarded AI program, and what I used to do was, when working with him, was take diagrams like this describing how safeguarded AI works and turn it into diagrams like this, which, as you can see, roughly matches the color coding, dramatically simplifies how you might go about seeing this. And specifically, if you, also worth noting, this diagram is from the Safeguarded AI program thesis. And so I spent a lot of time thinking about how to take a very complex, scalable proposal and start de-risking the highest risk subsets. And so this is another diagram of what it is Davidad is building, the order starting from this foundation level composable modeling language and specification language, which you can think of as a domain-specific language, plus Git, plus a CI for scientific theories, and building on top of that an implementation of this, AI tools to accelerate various modeling capabilities, proving capabilities. And then on top of that, you have these demonstrations that are probably narrow demonstrations. And what I am trying to do is say, it would be great to have a solid foundation and a framework that is generalizable and extensible and composable. Atlas Computing is throwing together a unstable stack just to show people, put this kind of thing in people's hands to demonstrate that if you have guaranteed safe AI in a narrow domain, you get interesting capabilities. You can learn how to use specifications and modeling and this kind of a workflow. And ideally, you pave the path for many people to follow towards something much more complicated that is more generalizable. And so in this specific model of having these narrower tools, the specific areas we're looking at are things like starting with cybersecurity. And specifically, this is the claim that if guaranteed safe AI works, then somewhere along the way, it probably got very easy to generate formally verified code. What do we what can we do in terms of onboarding people to a guaranteed safe AI workflow for verifying code now before we have generally intelligent capabilities or super intelligent software generation? Are there things that we can build that extrapolate the progress of language models but need to solve real human UX wetware type problems? I also think that there's a compelling exploration to be done in improving how we understand systems within biology or biochemistry. I think that there are interesting guaranteed safe AI opportunities for a narrow specification language in terms of our epistemic rigor and how we trace news and how we evaluate the robustness of arguments. I think there's probably something that we could and should be doing around formalizing aspects of legal systems, particularly things like tax code and contract law, that could be particularly compelling when we have AI capabilities scale to the point where a lot of contracts or a lot of taxable activity is done by AI agents, and we need scalable review and evaluation of those. And I think that there are aspects of society more broadly that are where there is systemic risk. It is unclear what form that will take and what form the solution could be, but it's an interesting area to explore and discuss, to think what would it look like to have a specification and modeling language for the kinds of societal systemic risks that we would expect from some general intelligence, even if not super intelligence. I will also note that a lot of the things that I am looking at are assuming moderately long time, not necessarily long timelines or slow takeoff, but a lot of the things that I will admit that a lot of things that we are pursuing are unlikely to be highly impactful if there are short timelines and very fast takeoffs, as opposed to many other approaches people are taking. So for each of these domains, the question becomes, what does this look like? I would claim that a lot of what people are doing looks like this generation of informal specifications and candidate solutions that get approved after human review, and we should have this more specification-based architecture. And because I'm not going to cover it outside of this slide, I wanted to briefly mention the concept of having a toxicity forecasting tool would help you understand, is this small molecule likely to be risky? You've seen experiments and demonstrations, publications where people have used AI-based tools to generate new materials or large numbers of neurotoxins. These are things that are based on inscrutable models for the most part within either inscrutable AI models or non-AI accelerated existing models, where it's the proposing of the molecules that the AI is doing, but it's not explaining why this is interesting in a meaningful, interpretable way. I will also note I am not monitoring the chat. Orpheus, if you see anything that's like a quick interrupt, feel free to unmute and call out those questions.
Sounds good.
So the specific proposal for a toxicity forecast is to have something that looks like a competition analogous to CASP, which is the experiment that AlphaFold became famous for. It's not a competition that AlphaFold became famous for not winning, in that it was labeled an experiment. But the idea would be you get a small molecule and you have some sophisticated AI system that says, here is how we predict that molecule will bind with literally everything we know of that exists in a human cell. And then you have a second system that will try to use those binding energies, reaction rate coefficients, other bioactivity parameters, and say, this is how toxic we think that molecule will be. And these are the main reasons that it's this binding energy, or it's this reaction that we think makes it or that the model thinks makes it toxic. And the nice thing about this is that this can now be tested in simulation or in a lab setting, and you can verify because these are physical measurable parameters as this intermediary output. The other thing you could do once you have, I know there are open science problems when it comes to actually building this thing, in the same way there are open science and novel science done in creating AlphaFold. I think that this is still important science to do that probably isn't something that we want to delegate entirely to learned systems. And if you have a system like this, you can start doing interesting things like having a natural language description of, I want you to generate a drug that could modify this pathway, do like reason by analogy potentially, and say, I want you to do for this enzyme what this other molecule does for this other enzyme, and add some constraint on what kind of harmful effects you want to avoid. I think it's important to note that this is a specification language, not a set of universal rules, in that what is toxic may vary by person, by country, by religion, things that you don't want to necessarily be prescriptive about, but there are probably some reasonable baselines that you can state, where opinions on alcohol may vary, on ethanol may vary, but opinions on cyanide may be more universal. And the specification would let you formalize into objective criteria what you mean by modify and harmful. And this could be potentially useful for future solution generators. I think that small molecules are safe in that there's low self-replication risk and things like that. So this is an area that I am interested in. We're not pursuing it as actively as the other area that I'll spend most of the time talking about, this direction of generating specifications for software and then generating software and proof that the software meets the specification. I imagine many people in this audience are familiar with formal verification, but I'll unpack this a bit more in the next section, in which I will be talking about our progress on this as our primary project. The biggest announcement is that we have recently soft launched this tool chain of tools that we think should be built, AI accelerated tools for generating formally verified software. The link is, I can drop the link in the chat because I think this is going to be generally interesting. And it might be worth having it to follow along on certain parts of it. This is the executive summary and the table of contents. But going through this diagram, this is kind of the main diagram that I use to structure my thinking about what's happening with these tools. And I highlight that you have, when you're generating software, usually some sort of intent and documentation and an implementation and an executable. And when you try to formalize software, you also have a specification, which is a much more rigorous theoretical statement of what that software should do, and proof being mathematical proof that the specification, or that the implementation does in fact meet the specification. You can demonstrate consistency between the specification and proof with proof checker. You can compile your implementation to an executable. And currently, the formal verification workflows look like generating the specification, proof, and implementation separately by hand as an individual. And so we've started doing explorations of how much of these generation steps can you do with language models. The toolchain document itself highlights this set of tools as the things that we think are the most compelling tools. There are definitely some subjective choices in here, but I figured basically I would go through and identify what these were and kind of how they fit together and how you might use them. It is like reasonable to look at this with the other components if you want to see it flow through, but I think for simplicity, I'll just show this as I talk through this. Here, intent is kind of what it's really the tacit latent preferences about how you want the software to behave, where documentation is a natural language description of that, of the software behavior. And so you could imagine writing up what you want software to do and having auto formalization and maybe even auto informalization workflow to iteratively improve the documentation itself. Or improve the documentation itself and get you a specification from that that will rigorously state how you want the software to behave. Interagent here is a tool that will help you identify between what you want and what you specified, whether the scope of the specification is strictly larger than the intent. If the intent is strictly larger than the specification, or if these are mismatched, this should help you understand what might fall into one of those, basically what the XOR of the two sets of program behaviors is. This is something that I think will need human interaction and is frequently something that I imagine many of you have either wondered or received as potential criticism of guaranteed safe AI systems. How do you know that the specification itself matches what your human intent is? And I think the answer needs to be some amount of sophisticated tooling that can help you iteratively understand the specification itself, because there isn't necessarily an obvious way to encode your preferences in all circumstances. Maybe for something like, does this piece of software self-replicate? That's easier to frame. Even that, I think, might be challenging without some hairy assumptions about the rest of the world. But there are probably some things you can specify there are definitely some things you can specify robustly and succinctly. There are many things where you should expect that to be harder to understand and encode simply as documentation without some iterative process. So those are the first three. There's also the fairly self-explanatory implementation to spec and spec to implementation. Many times in the wild, you're going to come across a legacy code base where you have an implementation, but you don't have a specification. And you'd probably want to be able to take that implementation, generate a specification from it, and then maybe generate a proof from that specification that the implementation matches. This may require regenerating the implementation from scratch, because oftentimes you'll have an easier time generating a proof if the implementation was made with the intent of formalizing it and proving it. And so these two become a pair of tools you're likely to iterate with. Once you have this formalized software system, you're almost certainly going to want to update one of these three, and that'll most likely be either the specification or the implementation, or maybe the documentation, which you formalize to update the specification. And in that case, you will want to make sure you have convergence between the specification, proof, and implementation. And that's the role of program repair, in which you say, this one was updated. How do you change the other two so that these are now synchronized? Program equivalence will give you will take two different implementations and give you some understanding and tools to understand if these two programs are the same. If not, why are they different? How is their behavior different? Inter framework, and I did not explain what framework or specification logic is here. I don't know. I think this is probably best saved for the discussion, but you can, in a hand wavy way, think of these as like, are you doing this in Lean, or are you doing this in Daphne, or are you doing this in Promisee? Interframework would let you take specifications, proofs, or implementations and map them from one framework to another. There's no good reason why you would want to have everyone dropping all existing libraries and tools from one framework in order to all dedicate themselves to a different framework. There are many instances in which you would want to prove something in one framework versus another. And so Interframework allows you to leverage the existence of tools and libraries and specifications and implementations in one framework in a different framework. And then the last tool here to name is this input output to spec, where in some cases you may not even have source code, you may just have an executable, and being able to convert this into a specification is something that you will probably want to do. This will use some amount of probing and some amount of decompiling in order to understand what the software is doing. So these are the main tools. If you have a very strong opinion and rationale for why there is a tool that should be here that is not here, be very interested to hear that. You can either email me or I think we're accepting comments in the report itself. Yep, anyone can comment. So try not to overwhelm us with comments. We are a small number of people, and also please don't be offended if your comment goes, if we do not make changes to this document in response to your comment, but we will read every comment that lands in this document. In addition to that diagram, another thing that I would point you to that is a nice compression of information is this table, which is linked from the document. Here it is in Google Sheets itself. We have brief description of each of the tools, these general themes in which we've lumped them for simplicity. We have these categories where we say, is this tech transfer? Is this a de-risking? Or is this an exploratory project, where we define those roughly as in terms of the probability of distribution, your probability of distribution of resources needed to complete the project. And so if it seems like a narrow distribution, we call it tech transfer. If it's broad, it's de-risking. If it has a long tail, we call it exploratory. Excuse me. We've estimated a minimum viable product and personnel required, funding, and time. And that's kind of to get us from the technological readiness level that we have now to some target that we've listed in this table. The estimate here is kind of highlighting the amount of low-hanging fruit we believe exists in the space. And the general call to action, which I didn't list here, is that we have, at the end of the executive summary, a link to a GitHub repo where we have not yet started to, but we will be collecting links to tools that do all of these things. We will sort them by the framework that they exist in, and I don't expect many of them to nicely match these interfaces at first, but I think that we will go through and try and build out we will try and build out some of these tools starting this month, and look forward to updating you on how those constructions are going. One thing to note is that this is kind of the bottom-up approach in which we are mapping out the pieces. And then the next step is not to go and immediately build all of those and assume that it will work and be useful and be used. I do not believe that if you build it, users will come. Instead, we are going to present this plan and some of these tools to potential users and identify their current pain points. This is one of the reasons why we may not take feedback into the roadmap now on this is the way this should be done, because that is much of that feedback might be overly theoretical and may not actually change whether or not people use these tools. And the main point of this approach is to familiarize more users and potential stakeholders, particularly users, maintainers and operators of critical infrastructure, because one, those are individuals who are sufficiently security focused that this might be interesting to them. Two, it would be very useful if on the path to general intelligence, we can improve robustness against sophisticated narrow intelligence that is being used to exacerbate cyber attack or cyber risk. And three, if this works, then, or if the general safeguarded AI approach works, then this seems like the simplest use case subset of that architecture that could then be expanded very meaningfully. So once we've identified pain points, we will start building prototypes that we put in front of them, we're starting to build prototypes now. We are expecting to radically change those if they do not address user pain points. The third step is that our target is to give users superpowers when it comes to generating software. I think this is a fundamentally better way to generate software, in that when AI systems are generating full libraries, it will not be reasonable to do code review on those incredibly large libraries to understand if they have every property, which are much easier to understand and get guarantees on succinctly if those libraries are formally verified. Worth noting, this is very much, I would claim, the bottom-up approach, which tends to have stronger guarantees of impact, but it tends to take longer time, or have longer timescales. There is also a top-down approach in which you would build a single tool that would maybe take an LLM API key and a Git repo link and output that repository rewritten in Rust and formally verified, for instance, using something like Varus. This seems like much more of a moonshot. This also seems highly complementary, and I'm interested in anyone who is considering or wants to try to run this moonshot approach from a research or engineering perspective. That's kind of the primary project progress. I did want to add some brief bonus content on this direction of hardware-enabled governors for compute governance, as this is something that I've been increasingly convinced is generally important. It's unclear the extent to which this will be a focus of Atlas or something I spend significant time on, but this seemed like an important group to share this update with in case you didn't come across it already. The starting point that I'll come at this from is that I think everyone here agrees that saying a particular model won't self-replicate because we tried it under controlled conditions might intuitively feel a lot like saying this railing is totally safe. Look how hard I can throw myself at it. And while guaranteed safe AI gives you something like the engineering load capacities and guidelines for and like engineering codes for how to install a safety railing, so you have high confidence in the safety of the system before you go and test it under conditions of consequence. There is also a question of, wouldn't it be nice to have a net beyond that or something so that even if the railing does break, we have something that we can rely on or trust in some capacity? And so there's this memo that I will also drop into the chat, where there's a proposal for flexible hardware-enabled governors. I particularly like this framing. You can't put an IAEA inspector on every U-235 atom to report if it's being used for weapons or power, but you could very much do something like that for GPUs. This is something that I think is slowly moving into the Overton window, and I would love to see people from this, the viewers of this talk, attendees here, to try and spread, like push on the Overton window just a little bit, spread awareness of what this could look like. I think this is plausibly critical to an international collaborative environment of AI development, as opposed to a world in which nation states start racing for superintelligence with their data centers underneath mountains. Slightly extreme as a take, but I think there are varying levels of, I think that there are versions of this proposal that are very reasonable, very plausible, and that most people would agree is generally a good idea. So with that, I will note that those are the slides that I made. I will share the link to these slides because there are some additional hidden things where you may want to revisit something. And other than that, I'll be happy to take questions. Looks like Steve has a hand.
Hi, great talk. Thank you. Very interesting. I'm thinking about your big picture in the software formalization and synthesis. And it seems like the auto formalization, auto informalization pair is a really nice little module that could stand on its own and could apply to basically any system. And I had a couple of suggestions for that. One is that you should make that process interactive. So you write a little English description, you give it to the system takes your English and tries to formalize it, but realizes there's ambiguity. It's got several different possibilities. If it can then query you, oh, did you mean this or did you mean this? Or here's an example which is different. That I think could be an interactive process for creating precise English descriptions would be hugely win. And then the second one is, I'm guessing there's going to be a library of specifications, particularly for safety. Somebody's going to have, the ultimate don't self-replicate library, the ultimate don't leak information library, the ultimate don't go into infinite loops library. And the specifier should know about all of those. And so when you say one of those, it can grab the best one, the best version, and incorporate it. So integrating with a library of specs, those two seem like, what do you think about that?
I absolutely love this library of specs idea. This is I think one of the most powerful things about guaranteed safe AI is this notion that optimization targets don't compose nicely. Restrictions on like state space do compose really nicely. I can say don't self-replicate. You can say don't create all these memory leaks. And we ideally create something that doesn't self-replicate and doesn't have all these memory leaks. And this perfectly mirrors how we implement laws for humans. And I think that once policymakers understand that you could presumably set specifications for AI in an analogous way to how we set laws for humans, where you have international standards that everyone agree, like don't self-replicate is not something you should be able to remove from these tools. Or if you do, it is with express permission by some international organization, in the same way that you can, yes, you can create, you can do gain of function research, but there's a set of criteria you need to satisfy. And there are real barriers to removing safeguards that are put in place. Similarly, you can own illicit drugs, or you can own controlled Schedule 1 substances in the US if you are a research lab. You need a license for that. You need lots of review. You should be able to say, I want this formally verified software to have access to literally all memory because it's searching for viruses. There are instances in which these things make sense. You don't want to always have these things as universal policies, but I think having almost universal requirements at every level that have human review processes to evaluate if an exception should be granted is a huge reason why I think this is such a compelling direction, in addition to the general, if two nation states are disagreeing over something like economic policy, then you can very easily set up an agent that says defect on all agreements, but it makes more sense to have a situation where you set a specification around what policy you want it to have, and then you have as much reason to trust that agent as your counterparty, because you're both using a spec and proof against that spec for the behavior. Sorry, that was a bit of a tangent, but a secondary reason why I think that people should find this kind of specification-based architecture very compelling.
Great, thank you.
All right, QD, I think you are next.
Yeah, this is Quinn.
Oh, Quinn, yeah.
The the last slide about generating like with an LLM key, API key, and yeah, like what are your thoughts about how you leverage like all of the effort that's going into this? I mean, the VC numbers on program generation are like pretty huge. So like this seems like something you could just let other people do or something like you know, like do you have any thoughts about how to leverage like effort that's going into this, not from um your point of view, but just like that's going into this anyway?
I've seen surprisingly little venture funding into formal verification, like auto formalization of software. I've seen some
Oh, well, that's
into,
true.
I've
Yeah,
seen
the
there's a lot of
generation.
venture money into code generation, and
Yeah.
I do think that, I mean, I will also note all of these things we're building, I think would be very venture fundable. There is a good question of why is Atlas Computing a nonprofit? And the answer is that I want all of this progress to be something that does not require a monopoly for everyone to be using it. If we build things that work and show better safety properties, they will probably also show better capabilities. This is something that we should realistically give to everyone who asks. We may have to build a for-profit just to get access to capital in order to scale to a meaningful size to be able to do some of these things, like advanced, like do fine-tuning enough to do proof generation or like have RL systems that do proof search. I think there's probably enough in the math community that we can leverage in proof search that we don't have to do much on our own. I would expect software to be potentially, I'd expect a lot of the breakthroughs to port between those. I do think that there's, I think minimally interactive software generation probably has a ceiling in how useful it will be because of this notion that once you've generated software, it will probably have like modal security vulnerabilities, and it will probably have quirky behavior that you did not specify because you didn't have this interaction between user and implementation, and you didn't have these libraries you could rely on that would meaningfully set a bunch of that would give you clean abstractions for describing categories of behavior, but instead are leveraging what's nearby in the embedding space. So I think there are interesting things to be pulled. I would love to partner with companies that are doing this and try to steer them toward this path, towards the path of doing more formalization. It's an interesting landscape. There's definitely a lot there, and I think there'll be a lot of like case by case nudges.
The only issue is that Prusty and Varus are like very premature prototypes, like for the verified part, for verifying the repo rewritten by the LLM. Like the tools we have for that for Rust are just like prototypes, but you know.
Yeah, and there I will note that there is a there's a staged approach to this this top-down approach as well, where you could say, all right, stage 0 is rewriting from like C to unsafe Rust, and then we will write from C or safe Rust to, or C or unsafe Rust to safe Rust, and then to verified Rust, and hopefully somewhere along the way, either we or others, either we directly or transitively have increased the attention on and efforts to expand the subset of Rust that Varus covers. David?
Yeah, thank you. This is great. Very excited about this class of work. I think that it's very promising. We've been having a conversation in the chat I think that this is very promising in contexts where it's not explicitly adversarial. I think that there's, in engineering, there's a joke, every time you make an idiot-proof system, they make a better
Becomes
idiot.
a better idiot. Yep.
Yeah. So there's a huge difference between, making a railing that is safe, and making a railing that somebody could not get over or through when they try. I think that the overarching vision here is if the superintelligence is actively adversarial, then you already lost. And a lot of what we're trying to do is build things that are safe and ensure that we can say intelligent things about these systems up to that point. But I'd be interested in your thoughts about, like, do you think the constraint-based approach is promising for explicitly adversarial systems, more limited? Yeah, interested in your thoughts.
I do put some amount of probability mass on if the superintelligence is adversarial, there's nothing we can do. I think specifications are a very useful tool in a toolbox. I would never say, like, all of this mechanistic interpretability stuff and like super alignment should be thrown out the window and we should go all in on guaranteed safe AI. I think that there are some things that are more likely to accelerate capabilities, and those I would feel good about there being less attention on at the if that's the trade-off to get more attention on guaranteed safe AI. But I don't think that there are. I'm not really a believer in silver bullets. I think that there may even be a meaningful continuum of misaligned superintelligence where this helps catch like minor misalignment. I think that it's much easier for people, maybe for historical reasons, to imagine a weak misalignment where you put a hole in the ozone layer, or you have your AI-driven economy doing something like that, and less going to turn you all into paper clips. And this approach seems very convincing following those risks. I do think that there's, like, speaking to the role of specifying constraints and not like there are really two main criticisms I've received of this plan. The first is, how do you know that you've actually specified what you want? So this is the intent spec gap. And then there's also the model world gap. How do you know that there isn't something missing from your model that is meaningful? And I've even like, people will say, like, when airplanes crash, it's because the model was incorrect. It's not because of the software. And it's because the like trust in the sensors was misplaced, or the assumption that the sensors were accurately reporting the world, or that the world would obey certain criteria. It was never a gap between the software and the software and the model. And I think this is a case of survivorship bias where it's formally verified.
It's also,
so of course, it's going to be on that side.
It's also never a gap between our understanding of physics and how the airplane works. Like, that's not where the failures happen. I think Davidad has said, like, this is not proof against AI discovering new physics. We're not going to be able to do that. But I think that, yeah, what you said makes a lot of sense. And I guess the last note that I have on this is, if we have the ability to formally verify things, then one of the things we formally verify is you're not attempting to build a system that is much more powerful right now. And that's something that we can specify much more easily than we can specify you're not trying to do something we won't like.
Yeah. Yeah, and I think that there are probably, like, there are human review tools that you will want and need to better understand the possible state space in the simulation. And I think that, like, the use of AI systems to do the anthropic mechinterp, like understanding of various clusters, forgetting very sleep deprived, forgetting the terms in the name of that paper. But I think that's exactly kind of like, we're using weaker AI to better understand stronger AI systems. And I think that we will definitely have tools like that that are maybe not wholly trustworthy, but at least fairly interpretable to help us understand how we are constraining the state space and how we are, like, if there are meaningful clusters that we're seeing in one set of possible simulations that are different in a way that might be meaningful to us. All right. Is there anything from the chat that I missed that would be worth exploring? Thank you, Daniel, for contributing. All right. Well, I believe that is roughly my time, actually. So I guess I will return to the last slide of where you can find me in case anyone is interested in that. My Calendly is open. I'm happy for discussions. I think that there may be interest in scaling these efforts from funders. And so at this point, if you have someone that you think should be working on this from a research or engineering capacity, please let me know. I think the funding is not guaranteed at this point, but it would be great to have people who could be pried loose from their existing commitments or when if and when that funding does come through. And other than that, I will thank you all for joining and hand it back to Orpheus.
Thanks so much for the presentation, and thanks everyone for the discussion. Yeah, that closes the session today. There is a mailing list about Guaranteed Safe AI, which you can find information on the Luma event, and stay tuned for the next one in August. Yeah, take care, everyone. Thank you, and goodbye.